Great. Great. Well, thank you. Thank you so much for everybody for being here. Thank you to the organizers for inviting me. It's so great to be here. I wish we could all be in Toronto, but nevertheless, it's so nice to be here with you today. I was looking at the list of participants, and I noticed that so many of you are people that I don't usually go to conferences with. I don't usually get a chance to talk to you. So, or maybe we've never met. So it's so nice to get a chance to talk to other mathematicians that are not necessarily community algebraists. And so I thought that maybe made this the perfect opportunity to tell you about one of my favorite topics that maybe you've never heard of before. So I thought I'd make this sort of an overview talk about symbolic powers. I'll tell you what they are. I'll tell you why I think they're interesting, or some of the reasons I think they're interesting. And then I'll sort of focus on some of my favorite open questions that people are thinking about. And I'll try to highlight some combinatorially flavored questions. So I won't go in depth into anything, but if you want more resources afterwards, I'll be happy to point you to lots of things. So throughout my talk, for simplicity, whenever I write R, it will be a polynomial ring over fields. Really, pretty much anything I say will hold over any regular ring, maybe sometimes containing a field. But this is already a pretty interesting setting to be in. So every open question that I'll write today is open over a polynomial ring over a field, even in 3 variables. So this is not a big restriction. And my ideals will all be radical. That will make the technicalities of the story easier to tell. There is a story for non-radical ideals, but again, these are already interesting enough. Even the story for primes is already quite interesting. So a radical ideal is something I can write as a finite intersection of primes. So I might as well take just the minimal primes of I. I'll call them P1 to PT, and I'll use those components to tell you what the n symbolic power of I is. But maybe let me start by telling you the definition for a prime ideal. So if P is prime, the n symbolic power of P, so notice here I told you, this is the notation that we use for the n symbolic power of an ideal. The n symbolic power of a prime is the set of elements in a ring that live in the ordinary power. So here's a reminder of what the ordinary power is, up to maybe multiplying by something not in P. So I'm really saying in the localization of P, I live in the power of the maximum ideal. And so more generally, for my radical ideal, the n symbolic power is obtained by computing the symbolic powers of each of these components. That's the same thing as asking about the elements that are sent now in the power of I, up to multiplication by some element who is not in any of these minimal primes. Okay, if you remember anything about primary decomposition, what I'm really doing here is I'm looking at the power. I'm writing a primary decomposition for the power, and I'm collecting the minimal components and ignoring all the embedded components of the power. So there are many reasons why you'd care about this. They are very closely related to ordinary powers. I guess you can see immediately from the definition, one is not in not in my prime or not any of these guys. So it's automatic from the definition, this contains the ordinary power. I'll tell you soon, they're not necessarily the same. But go ahead. Sorry, I don't have my chat.
Somebody's asking if you can rewrite the condition on S somehow without primes. Like if you view it as a coprimality, SR plus I to the n equals 1.
I don't think so. I have to think about this a little bit, but no, I don't think so. Because this would say, so are you suggesting this would be maybe the set of S's that, oh, I'm sorry, your capital R is not all of R. Do you mean, so do you mean the set of little S's such that the ideal generated by S would be 1 mod I to the n? Is that Am I reading it right?
Sorry, this is probably not the right condition, but what I want is to avoid the prime decomposition to make it a bit more homomorphism friendly. So
this is okay. It's not very homomorphism friendly, but it's coming from a homomorphism. What's happening is this is, you took the power out of the n and you localized at each of these primes, and then you contracted that image back. Does that make sense? So you took out of the n. This is how you normally would write it. I was maybe avoiding writing that. I thought it would be less clear, but maybe it might be more clear. So you take your power, you localize it each of these minimal primes over I, and then you're going to contract back to R. This means a contraction, so the pre-image in R of that. Okay, it's completely equivalent to writing this. Okay, good. More questions I should answer for now?
No, that was it.
Okay, very good. So let me tell you maybe a geometrically flavored reason to care about symbolic powers. So here's a classical result of Zariski and Nagata. I'm going to write it over C, but there's a version of this over any perfect field. I'll just want to make things less technical to write down. So the n-symbolic power of my radical ideal is what I get when I look at all the maximal ideals that contain I. So think points in the variety that I determines. And I want to be in all the powers of those maximal ideals. So this is saying these are the polynomials that vanish at all the points in that variety to order n. So they don't just vanish, they vanish to some high order. So a different way to say that, this is the set of all the polynomials that when I take their partial derivatives, so this is why I wanted to write this over C, but you know, the right notion of differential operators, you can write a definition over any perfect field for which this is also true. So I take any partial derivative of order, okay, I didn't leave enough space, sorry. Let me move this. So I'm going to take any partial derivative of order up to n, and I want the resulting derivatives to all still be an I, so to all still vanish on that variety. So for example, from this you might see that when you take the first symbolic power, you're not really doing anything here, right? This would be smaller than 1. And so you're just saying, hey, it's the things that are in I. So the first symbolic power is I. Right? But then the second symbolic power would be things that are in I and their first partial derivatives are also in I. So again, this is saying these are the polynomials that vanish to order n on the variety that I defines. Maybe as a side note, curiosity, I'm going to mention that even though today I'm talking about fields, if you want to do something like this in mixed characteristic, this description that I just gave you is not quite right. So say, for example, if you want to replace my field K with Z, so this description of the symbolic powers is not correct. And sort of the point is that these derivatives only see what's happening in sort of the geometric direction, and they don't see what's happening in this arithmetic direction coming from Z. So you have to add in something else to do that. I know I'm being extremely vague here, so take this as a side note. But so as a side note, let me tell you, there's a version of this over Z. That's a joint work with Alessandro De Stefani and Jack Jeffries. Oh, that's so funny. I was talking and not looking at what I was writing, and I did not write what I meant. Okay. But today I really want to tell you the story about fields. And so maybe let me start with some simple properties. So one property of symbolic powers I've already listed is that they contain the ordinary powers. And if you think of this, at least believe this description, that is the things that vanish up to order n on the given variety. then if I vanish to a higher order, I also vanish to a smaller order. So this is sort of a nice nested family of ideals. And it's in fact a graded family of ideals. So when you take something that vanishes to order A, you multiply by something that vanishes to order B, it vanishes to order A plus B. So in fact, this third property is going to tell us that you can build a graded object out of this. If you were to Selvi's talk this morning, she was talking about Riesz algebras. You can build something called a symbolic Riesz algebra out of this. So this is the graded algebra that in degree n has the n symbolic power. The zeroth is just r, right? So like in her talk this morning, this T is sort of keeping track of degrees. And maybe I'll mention a few more things about this symbolic Riesz algebra in a little bit. But let me tell you that sometimes these symbolic powers are the ordinary powers. So the easiest to state such results if that if I is a complete intersection, so if the codimension of that variety, the height of I, is the same thing as the minimal number of generators, this means minimal number of generators of I, then in fact, the symbolic powers are equal to the powers for all n. But this is very far from being exactly the situation where you have equality, right? This is just a sufficient condition for you to have equality. On the other hand, I want to show you some simple examples of ideals whose symbolic powers are not powers. Is there maybe something in the chat? Sorry, I close it again. Is 2 and 3 going in the opposite direction? No, they're both going in the correct direction. So to be clear, I'm saying that, for example, something in the second symbolic power lives in the first symbolic power, which is I, but this is smaller, right? Because you want, see, maybe it's easier seeing from here. This is saying that you want something that F is an I and also that its derivatives up to a certain order are all in I, right? So this is sort of growing in conditions, so giving you smaller and smaller ideals. And same thing with 3. It's also this is the smaller ideal over here. Okay, good, very good. I'm going to try to keep the chat open here. Hopefully, I notice if it comes up again. Okay, so example. Let's take the monomial ideal generated by xy, xz, and yz. So I guess I m and k adjoin xyz now. K, what k is doesn't really matter for what I'm about to say. This is, of course, the union of the 3 coordinate lines in a affine space. So each of those coordinate lines give you one of these minimal prime components. In fact, this is I just wrote down a primary decomposition for I. And if you want to write the second symbolic power, what I set up there was, I know we don't see it anymore, but I'm going to take each of these components and write their symbolic powers and intersect them. But these guys are, of course, complete intersections, each one of them. So for each one of these pieces, the symbolic power is just an ordinary power. On the other hand, powers and intersections don't commute, right? So this is not just the square of I. So for example, the element xyz, you can easily see is in all of these things, right? For example, xy is in here, xz is in here, yz is in here, right? On the other hand, so reminding you, this contains the square, but on the other hand, this is an element here of degree 3. I is generating degree 2, so I squared is generating degree 4. So there's no chance. So this thing is not in the square. So here's an element that witnesses the fact that this symbolic power is actually bigger than the square of this ideal. Here's, okay. I'm going to do another example, but maybe this one I'll do quickly. So let's say that I take a 3x3 generic matrix. So R is the polynomial ring over the variables in that generic matrix. And I is the ideal of 2x2 minors over that, of that generic matrix. The determinant of this matrix, I claim, is an element in the second symbolic power, this ideal. So why is that true? Well, I can show this in different ways. Maybe for fun, I'm going to use this theorem over here that tells me that it's about things whose partial derivatives up to a certain order are going to be in there. So if I'm talking about the second symbolic power, I want to take first derivatives. I think we all believe the determinant is an I already. That doesn't need checking, right? I just need to check that it's first derivatives all live in there. So let me, for example, do it for the first. I'm going to do it for one variable, and it's the same story for all of them, right? If, for example, I wanted to think about x11, right? I'm going to, I mean the variable that appears in position 11 in my matrix. Let's do cofactor expansion on the first row of the matrix. So this is the first term that I get, right? And then I actually don't care what the rest is. Let me just say these are things in other variables, by which I mean there's no x1 in the rest of it, right? When I write the rest of the expansion. So when I take a derivative with respect to x11 of this determinant, I'm going to get, again, this. In fact, let me do some copy pasting. This is one of the advantages of being on Zoom. Might as well use it. And then the rest of it is 0, right? So this is obviously an element in I. So the first derivative is now, repeat with all the other variables. The first derivatives are all in I as well. So this tells me that indeed the determinant is in the second symbolic power. But again, there's a degree story going on here, right? It has degree 3, and I is generating degree 2 because it's given by 2 minors. So again, this determinant is not an I square. So this is something you see a lot when you have a homogeneous ideal. Its symbolic powers are homogeneous, but they often have things that sort of live in degrees you were not expecting, right? That are not matching the degrees in the ordinary powers. So as I promised, my real goal is to tell you about some, let me call them, maybe this looks, too serious, but these to me are sort of the big questions that we wish we understood. I mean, there are others, but I think these are some of the first big questions on the topic. So I think the first question one would ever ask, well, okay, one could ask, how do you compute symbolic powers? That's actually hard, because computing primary decompositions is hard. So computationally, it's a difficult problem to find symbolic powers. And so one of the dreams is, there are situations where we know better ways to compute these. And so one of our dreams is, getting good, efficient ways of computing these things. But so, modulo that's sort of what makes the big questions difficult, I guess. The first question you ask is, when do you have equality, right? So when is it that the symbolic powers are just the powers? Because powers are easy to describe, right? Symbolic powers are not. So if they're equal, life is beautiful, we understand everything. And of course, you might mean this question, I'm writing it vaguely because you can make this precise in different formats, right? You might be asking, for given an ideal, for which ends do I have equality? You might be asking, for which ideals do I have equality for all n? Can you characterize the ideals? Maybe let me write that down. So more precisely, can you, for example, characterize all the ideals I that have equality for all symbolic powers? And that's a very difficult question. There are several sufficient conditions that we understand. There are few characterizations of equality in particular, there's a nice theorem of Hoxer from the 60s that gives a sequence that gives us an equivalent condition to this equality that doesn't involve anything about symbolic powers. But the truth is that this condition is really hard to test and practice. In fact, in his original paper, he uses this condition to sort of applies it to several classes. And they're all of them now, now we have other reasons to explain why that equality holds there that are easier, right? So that technique of it is sort of difficult to apply. So I would say we don't have an easy, clean, simple to apply answer to this. There's no simple test I can do of an ideal to decide if this is true or not. So maybe what I mean by simple test, an example of what would be a simple test is if there existed a point such that if you found that you had equality up to that fixed point, so for n's up to d, that would imply equality for all n. If you can find such a d, if you prove, oh, I only have to go up to this point, that would be wonderful, right? Because that would at least be a finite test, even if the calculations were hard. And I want to tell you, even for the case of square free monomial ideals, we just got an answer to that very recently. So Jonathan Montaño and Luis Núñez Betancourt now officially a 2021 paper, so very, very recent. They show that if you have a square free monomial ideal, then the answer to this second question is yes, there is such a d, and they found what that d was. So this is a square free monomial ideal, and mu, as before, is going to be the minimal number of generators. So let me remind you, minimal, sorry for the shorthand, minimal number of, let me write gens of I, okay? And that's essentially the number, okay, that's what we need to say what this number d is. Their theorem is that if you've tested equality up to this minimal number of generators over 2, then you actually have equality for all n. So I really like this theorem. I think it's very nice, but notice how recent it is. And I should say symbolic powers have been around, almost as long as primary decomposition. So this is maybe a 100-year-old question. So not exactly, I think it's sort of surprising how long some of these things take to come about. So I thought I would tell you about a combinatorial flavored problem that's related to this. So this packing problem that I want to tell you about, it's an open question, and it's essentially a conjectured characterization for which square free monomial ideals have this equality. Right? So a combinatorial condition on the ideal that would say you have equality for all n. And so to tell you what the conjecture is, I actually have to first introduce a little bit of terminology. So I want to think about regular sequences of monomials inside of I. So you know what a regular sequence is? I specifically want not just a regular sequence, but one that's made of monomials. So an easy way to describe what that means is I want a sequence of monomials in my ideal that have no common variables. That's essentially what this means. And it's a simple fact about regular sequences that, let me just say, the length of such a sequence, so any regular sequence, not even of monomials, inside of I, its maximal length is the height of my ideals, the codimension. So I'm particularly interested in ideals for which this maximum value is attained. So I is Koenig if, let me say, if we have equality, right? So I has a regular sequence of monomials of length equal to the codimension. So maybe let me give you a simple example to give you a sense of how this works. That ideal we saw earlier, xy, xz, yz, if you try to pick out monomials out of here, of course, they're all going to be multiples of each of these three. And any two of these already have common variables among them. So there is no sequence of monomials that is regular of length 2, which means that this maximal length of such a sequence is actually 1, but the codimension of this ideal is 2, right? This is a union of lines in 3-dimensional space. So in particular, this is not a conic ideal, right? This is an example of something that's not conic. And I'm sorry for having to introduce so many names, but the key thing is to tell you what is a packed ideal. So being packed means the following. You started with your I, and you're going to create a ton of ideals out of I. You're going to look at all the ways to all the ideals you obtain when you set some variables equal to 0, some variables equal to 1, and maybe do nothing to some variables, right? So all of these, the number of variables that happens to could be 0, could be all, right? So look at all the ways you can do this, all the resulting ideals. If all of those ideals are conic, meaning if for all of those ideals, they actually contain a regular sequence of monomials that has the maximal possible length, then I'm going to say the ideal is packed, okay? And the conjecture this is called the packing problem, is that you have equality of all symbolic and ordinary powers if and only if I is packed. Let me give you a view of everything I wrote here so that the conjecture is clear. Maybe I'll even take this as a chance to move things around a bit. So this is an open question, but it is solved for edge ideals of simple graphs. So this is a theorem of Gettler, Valencia, and Villarreal. I think 2005. Let me look up my notes. Yep, 2005. And so this theorem, let me say it like this, it's true when I is the edge ideal of a simple graph. So to be sure we're all on the same page, I mean, you take a simple graph, finite, you number your vertices. Each vertex is a variable in my polynomial ring. And if you have an edge from xi to xj, then you put in xi, xj as one generator for your ideal. So these are square-free monomial ideals generated in degree 2. And for those ideals, the packing problem is true. So they're symbolic powers of the powers if and only if the ideal is packed. And in fact, they also prove that in this setting, this is equivalent to G being a bipartite graph. But the general problem remains open. So yeah, I think it's a good question though. All right, so I want to tell you a little bit about some other fun problems. Sorry, I'm here making a time decision. Okay, let me tell you about degrees. So I in the examples I showed you before, it happened in both of them that I had the way we convinced ourselves that the symbolic powers were not the powers was by finding elements in the symbolic powers that sort of lived in strange degrees, right? Degrees that you don't see in the powers. So that tells you already that symbolic powers can be generated in interesting, new, unexpected degrees in some sense. And so I would love to know what are the degrees that you see in a symbolic power. So let me for a little bit only talk about homogeneous ideals. And I'm going to denote by alpha of I the minimum degree of a non-zero homogeneous element in I. So the smallest degree of something we see in I that's not zero. And so very vaguely, right, a question I'd love to understand is, what is the smallest degree of something in a symbolic power? And note, I said earlier, the symbolic powers always contain at least the ordinary powers, just potentially bigger ideals. So notice this automatically tells you that the smallest degree of something in the symbolic power is at most the smallest degree of something in the power. And as we've used today, that's just n times the smallest degree of something in I. Okay? So upper bounds are sort of easy. The interesting question is giving lower bounds, right? Telling me how low can the smallest degree be? And even in the special case of finite sets of points in projective space, we don't know as much as we wish about this. So let me tell you about that special case. So I'm going to have S many points in projective space, and I'm going to think about the ideal of those finitely many points, right? So if you like, it's the intersections of these guys. And really, I'm writing a primary decomposition for this. And these guys are generated by like the sequences. So actually, the symbolic powers of this guy are just the intersections for sort of elementary reasons. They're just the intersections of the powers of the ideals of these finitely many points. So again, homogeneous polynomials that vanish to order n at these finitely many points. I'd love to know what's the smallest degree of such a polynomial, or give a lower bound for what that degree should be. And there's several conjectures to mention. I'm going to tell you about one and one that has had some recent developments. So this is a conjecture of Chudnovsky's. So from 1981, so about a 40-year-old conjecture. So now I'm in this setting, okay? My I corresponds to a finite set of points in projective space. And it conjectured a lower bound for this n symbolic power. Well, so the symbolic powers are, as we've been saying, so closely related to the powers that the first natural thing to do is to compare the growth of this degree with the growth of the ordinary powers. So the growth of the ordinary power would be n times alpha of I. I'm going to forget about the alpha of I, right? But think of this quotient as sort of measuring growth of this degree as n goes up. And the conjecture is that this is at least the minimal degree of I plus n minus 1 over n, where this capital N is the dimension of the projective space I'm in. Now, I've made a decision that I am, I could tell you more about this conjecture and try to motivate, where does this come from? But it would take me a while to sort of give you a sense of where this is coming from. I sort of decided to tell you about another problem instead. So maybe for now you believe me that there are good reasons why one would conjecture this, right? And there's lots of evidence towards this conjecture. So maybe if you believe this is a reasonable question to ask, and that has had multiple advances over the years, maybe I'll tell you about the most recent development that I'm aware of. So this is some joint work with Senkanil Bisuli, Tai Ha, and Tai Nguyen. This is funny to write, but this is going to officially be a 2022 paper. At least I'm told it's being published online in the next few days. So the theorem about algebraically closed fields, but it is actually true in any characteristic. Right? So this is something, what I'm about to tell you is true in characteristic P as well, if the field is algebraically closed. And maybe I won't repeat the conjecture. I'm going to write that our theorem is that the conjecture holds if you have, so first of all, you need a sufficiently large set of points. So you need at least 4 to the n points. And you need them to be general points. So this means the following. This means that if you fix the number s of points that you have, there exists an open dense set in the Hilbert scheme of s points where the conjecture holds. And so in a way, this is saying, if the conjecture is false, a counterexample is somewhat special. Right? So this is sort of something that generally happens. Now, how does one study something like this? Well, there's lots to say about it, but I'll say that the main ingredient that goes into this theorem is actually studying containments of ideals. So it's to somehow realize that this inequality, this lower bound for these degrees, is going to follow from some containments between ideals. And there are various containment statements that one might study. So I'm going to tell you about the containment problem. What we actually study here is not the containment problem. It's a variation on the containment problem. But anyway, the containment problem is something about containments of ideals, and it's related to what goes into this. Maybe I have time to say this. Before I tell you about the containment problem, which is the problem I'm going to end with, I will briefly mention that there's another fun question. So earlier I told you that one can consider this this symbolic Riesz algebra, right? So this, if you like, this is a subalgebra of R joined T, right? Where this T is just keeping track of degrees. And you might ask, is this finitely generated as an algebra over R? Which, by the way, is equivalent to asking, is this ring an invariant ring? And the simple answer is not always. And that deciding when this is finitely generated or not is actually quite difficult. And the idea is that saying this is not finitely generated as an algebra is saying that when you go at higher and higher symbolic powers, you're going to keep finding elements in your symbolic power that don't come from the lower degree symbolic powers, right? So if you remember early on, when I told you this was a graded family, I wrote this statement over here. And this tells us that, if you go to, say, degree 4, you will get elements coming from degree 2 and 2 or degree 1 and 3. But you might also get new elements, right, that weren't coming from all those products of smaller symbolic powers. And so saying this symbolic Riesz algebra is not finitely generated is saying that for arbitrarily large symbolic powers, you'll still see new unexpected elements. I will say, though, that the answer is yes, this is always finitely generated for monomial ideals. And that's a result of Lebesgue. So for monomial ideals, this is not this is a solved problem. But in general, there are examples even of primes of height 2 in free variables. So really nice, simple things in polynomial rings where this is not finitely generated. Okay, now, it is time for me to move on to the containment problem. So it has something to do with containment. And very vaguely, the question is, when's a symbolic power containing a power? So I do know this symbolic power always contains the corresponding power. I'm asking about backwards type containments. And there are many reasons why these are interesting. For example, notice that if you had such a containment, then that would say that the smallest degree of something in the symbolic power would be at least the smallest degree of something in that power. So in particular, solving things like this helps with lower bounds, right? And if you remember, when I was just talking about this result over here, I said, we study some containments. We study some, not exactly containments of this type, but other types of containments. So symbolic powers contain in something more complicated than just the power that end up giving you the right inequalities. But anyway, there are other reasons also, but this is maybe a good motivation for this question. And in our setting of polynomial rings, there's a beautiful theorem proved by Einlaserfeld and Smith over C and Hawks and Hunicke for the case over any field. And now recently I said I was only talking about fields, but I couldn't stop myself from adding this. It's also true in mixed characteristic. It's a theorem of Mann-Schweid. It's really a theorem about regular rings. And maybe I'll say, Mann-Schweid had a technical assumption. They needed an excellent ring. And Takumi Murayama has just posted a paper on the archive last month, I want to say, just a few weeks ago, removing that excellent hypothesis. So I'm really going to tell you a theorem that's true over any regular ring. But I'm going to write it. Maybe we can think about the polynomial ring case. So remember that early on, right in the beginning of the talk, I wanted to think about those minimal primes of I. Okay. And I'm going to need to look at those primes. And I'm going to need to compute the maximum of their heights. So if you ask for the codimension of I or the height of I, that's the minimum of the codimensions of all these pieces, right? So this is a similar but different invariant. It's called the big height. So for a prime ideal, it's just the height or the codimension, but in general, it's something slightly different. And this is the invariant you need. The theorem is that the Hn symbolic power is always contained in the n power for all n. So it's saying something really beautiful. It's saying that the answer to this question is linear. That on its own, that this was a linear function, that was already a theorem of Jonas Swanson from 2000. So right before this work. But her theorem was very, very general. It essentially said that when you have an answer to this question, that answer is linear, but it didn't tell us what the constant should be. And it was a constant that it was some magical constant, right? And these guys said, haha, if I'm over a regular ring, or if you like, I'm over a polynomial ring over fields, that constant is this big height thing. So for a prime, it's just the height, just a codimension. So for example, in that ideal from the beginning of the talk, x, y, x, v, y, v, this h, it's again, remember, it's a union of three lines. So they all have codimension 2 in three-dimensional space. So the h is actually 2. And here the theorem then says that 2n symbolic power is always contained in the n power for all n. So for example, it says the fourth symbolic power is contained in the square. Together, we showed that the second symbolic power is not contained in the square, right? Because they're different. So this is very close from being the end of the story, but I'll tell you that actually you can do better. Actually, the third symbolic power, which is a slightly bigger ideal than the fourth, is also contained in the square. And that's the best possible answer there. So the dream would be to answer this from a best case scenario, because in particular, it would give you better bounds if you wanted things like degrees. And Harborne conjectured, okay, if you were here, maybe would say, well, it was really a question. He really wanted to know, what was in the back. He knew it couldn't be the answer. He knew it could be, and he wanted to know, like, what happens, like right in the boundary of what I don't know. This is something from 2008. he asked if you could take this containment. So let me show you. This was the containment from these guys. So what he asked was, let's take the containment over here. Could I make it better? So could it be that I can always subtract h minus 1? So in this setting, here h is 2, so h minus 1 is 1. So this is exactly, this example is saying, well, yeah, here you can. And there are good reasons why one would suggest this. One very good reason, I think, one I think is very compelling, is that in Hoekstra and Huenicke's work, so what they did was they proved this over every field by proving it in characteristic P, and then using reduction to characteristic P to get the equicharacteristic 0 setting. And in characteristic P, what they showed is that if you think not of any n, but specifically of powers of P, so let me maybe call it Q, then they show that the HQ symbolic power is not just contained in the Qth power. This sort of what's at the key piece of their argument. It's even contained in the Qth Frobenius power. Doesn't matter what this is for the story, but I'll tell you, it's the ideal generated by the honest Qth powers of things in I. And so proving this was the key points in their argument. And it's one of my favorite arguments ever, because in some magical way, what you do is you do some really clever reductions, and then you realize that at the end of the day, all you need to do is use the pigeonhole principle. So to me, this is the coolest ever version of the pigeonhole principle, is this theorem here. But if you apply the pigeonhole principle carefully, actually what you can do, you get exactly the linear function from Harborne's conjecture. And the mysterious, incredible thing to me is that this doesn't force it to be true for all n. In fact, I won't let us believe this for much longer, because this Harborne's conjecture is not true for every n, for every ideal. And the first counterexample was found by Dumnitsky, Schoenberg, and Tatai-Gazinska. And if you like, I can write the ideal for you after the talk. It's not that it's hard to write. It's that I guess it's surprisingly simple. But maybe the point that I want to make right now is this is not true in general. In fact, they found a set of 12 points in P2. So the corresponding ideal is an ideal of height 2. This H is going to be 2. And it fails the third symbolic power in the square. So sort of the very first step in Harborne's conjecture. But mysteriously, it does satisfy the containment you want for all other n's. Let me maybe finish by telling you, though, that Harborne's conjecture is true if you ask for your ideal to be nice enough in some way. So many nice classes of ideals do satisfy this. And in particular, in joint work with Craig Huenicke, we showed that if the ring that I defined, so if R mod I is a nice ring, so something called F pure in characteristic P, then Harborne's conjecture holds. Maybe I'll say, okay, rather than defining what this means, let me tell you that this is some way of saying that the singularities of R mod I are really nice. So it's some measure of niceness. So rather than writing a proper definition, let me write some classes of ideals where this holds. So I'm going to write you classes of ideals that are F pure. I should say this is a condition in characteristic P. It's a condition on the Frobenius map. But there's also a characteristic 0 version of this. So this would be of dense F pure type in characteristic 0. And our theorem also holds in characteristic 0. But it's a sort of a reduction characteristic 0 type thing. But the point is the examples I'm about to write are characteristic independent, right? This holds in over fields of characteristic P or characteristic 0. So it does hold when I is a square-free monomial ideal. That was known before our work. That's actually easy to prove. That's essentially the pigeonhole principle again. But I think of these sort of ideals defining as pure rings are kind of a nice generalization of square-free monomial ideals. Lots of things that are true for square-free monomial ideals are true more generally for this class of ideals. But this also includes things like ideals defined by the T by T minors of some generic matrix, or ideals defining Veronese rings. So algebra generated by all the monomials of some fixed degree and in some fixed number of variables. I'm on my last few seconds. Maybe I'll say this. One thing I'm really enjoying about this conference is hearing about all these things I don't usually hear about. So in the last few days, I've heard a lot about Schur varieties, which I didn't know anything about. So I've been learning lots of nice things from several of you on that topic. And this got me, looking things up about Schur varieties. I was curious. And one fun thing I found out today is all the local rings of a Schur variety are F pure. In fact, they're better than that. There's something called strongly F regular, for which we can say more than this. But I'm out of time, so I'll stop there. Thank you so much.
Let's thank the speaker. Are there any questions? You, Thomas, has a question?
Yeah, thank you. Thank you for the lovely talk.
Oh, thank you.
I was wondering, and I'm sorry, this is maybe the answer may be very easy, but is the condition that a monomial ideal be König, is that like a simple, can you phrase that in a totally combinatorial way? Like, a statement about the sets that in the monomial and
yeah. Yes, okay. So I completely honestly, I think the answer is yes, but I could not answer it right now. Because the truth is I'm not a combinatorialist, so I don't usually think about the combinatorial side of these things, right? So in a way, when I think of this problem, I don't think about it in the combinatorial sense at all, right? So I know the answer is yes, but I couldn't out of the top of my head tell you right now what it is. I know that with maybe 5 minutes staring at something, I could tell you what it is. So yes, all these things could be, actually, here's a fun fact. So this problem is a restatement of a different problem. And that other problem, I don't understand. It's a restatement of a completely combinatorial problem that maybe you'll be familiar with. So it's a restatement by these three authors, by Gittler, Valencia, and Villarreal. So they're the ones who sort of converted that combinatoric expression into this problem about symbolic powers. And it's a conjecture of Conforti and Cornuejos about, I wouldn't say max cut min flow properties. I hope I didn't switch the order of those words. And I confess, again, I don't work in combinatorics at all. So I couldn't possibly tell you right now what the problem is. I know I've read it before, but I don't think about the combinatorics of it. But if you are familiar with that problem, I can tell you that solving this packing problem about symbolic powers is equivalent to solving that other conjecture. Oh, and so, yeah, I think that's very cool too. Even though, as I said, I don't fully understand the combinatorial problem. So I think, this is maybe one reason I wanted to talk about this today is that, maybe sometimes, different communities in math are working on the same problems and sometimes we don't know, right? And this is actually how this theorem of these guys came about, right? Was they understood how to convert this problem into commutative algebra and then solve some of it in commutative algebra. So I guess this says some of that other problem is also solved, and I couldn't tell you how it translates. But yeah, anyway, thanks for asking that question because you let me give a plug for that cool story. Thanks.
Thank you.
There's another question from Alan Knudsen.
Hi, this is a basic Frobenius thing that I'm sure I heard at the point, but the F purity you were mentioning at the very end, that holds in the Schubert situation. Is that because Schubert varieties are Frobenius split? Is that enough?
It's because they're globally F regular.
Does that tie into Frobenius? So the only part of the F stuff I know is about Frobenius splitting, and I want to know how close.
So F pure and F split are the same thing when you're over a perfect field. So anytime that your ring is what's called F finite, which means that it's a finitely generated module over itself over Frobenius. Every time you have an F finite ring, then F pure and F split are completely equivalent conditions.
Okay.
And this strongly F regular thing that I just mentioned very quickly implies F purity. So it's something stronger than F purity. And that's actually what these local rings of Schubert varieties satisfy. So they satisfy something better. So roughly speaking, the idea is not only are they F split, but there's lots of splittings to the Frobenius map in some very concrete sense.
Sorry, when we were over a perfect field, then which things were equivalent?
I'm sorry, that was a lot to say without writing. So F pure and F split are equivalent conditions. So this means the Frobenius splits as a map of our modules.
So
you're
over a
asking
perfect
me
field,
about
these are the same, and over an imperfect field, the left one is better?
over an imperfect field, the left one's better. That's right. That's right.
Okay, thanks.
Very good question. You're welcome. Sorry, if I'd had more time, I would have written a proper definition, but I was right at my last moment. So good question though.
Are there any other questions? Let's thank the speaker again.